Hello everyone. In the module 6, we are going to discuss the importance of differential pulse code modulation techniques. In the module 4 and 5, we have discussed the SNR calculation of PCM as well as the importance of compounding in PCM. Now we can find one of the drawback of existing PCM system. So in order to overcome that, in this module we are going to discuss the differential PCM system. So coming to the PCM system, we have calculated that the bandwidth required for PCM system is n into FM, where n is the number of bits grouped per sample and FM is the bandwidth, maximum message signal frequency. So with this, we can conclude that the PCM system bandwidth is completely dependent on the factor n. In order to improve the SNR, you need to improve the value of n. But once n increases, the PCM requires large amount of bandwidth. This is the first drawback of PCM system. So PCM system needs a large amount of bandwidth for signal transmission, and it is equal to n always greater than or equal to n into FM. And the second difficulty with the PCM system is the encoding, decoding, and quantization process. The process is completely complex. So in order to simplify that, we are going to move to the differential pulse code modulation circuit, which will reduce the ambiguity in the PCM. And here the quantization error attained from PCM system can be somewhat reduced by using DPCM technique. In the DPCM, we will use the prediction filter that will eliminate this quantization error. So three main drawbacks are there. One is regarding the amount of bandwidth. So large amount of bandwidth is required. And the second one is the encoding and decoding process of PCM is somewhat it provides some sort of ambiguity. And third drawback is here the occurrence of quantization error. These three can be eliminated by using the uses of prediction filter in PCM system. And coming to the response of, here you can see, this is the response of PCM system. For example, if you consider x-axis as the input sample signal and y-axis as the quantized amplitude signal, at each and every interval you can observe, for example at t is equal to ts, you can observe the maximum amplitude of the respective signal. It is equal to 2. At 2 ts you can find the amplitude as 4. Similarly at 3 ts you can observe 5 volts. Similarly 4 ts, 5 ts and 6 ts you can observe that the amplitude is almost all there is a gradual change in the amplitude of message signal. So it is almost all approximated to amplitude 6. That means here you are transmitting this 110 3 times. So thrice you are transmitting. So this is the main drawback of our PCM, existing PCM system. In PCM, we will transmit the redundant information. So similarly at 7 TS, 8 TS and 9 TS, you can observe that. Similarly, you can observe at 7 TS, 8 TS and 9 TS, the amplitude is 101. So same amplitude is transmitting thrice in the same case as 4 TS, 5 TS and 6 TS. This redundant information is transmitted in PCM system. So in order to overcome this, we are similarly at 9 TS and 10 TS. At 9 TS, the amplitude is 101 and 10 TS, the amplitude is 100. The difference lies only in the last bit. Here you can see the difference lies only in the last bit. So this is one type of transmitting the redundant information, because the PCM transmits each and every sample, each and every amplitude of the sample will be transmitted. So these are all the advantages of PCM, but the main drawback is its bandwidth, because of it needs large amount of bandwidth, and also it transmits the redundant information, and it has quantization error. To overcome all these drawbacks, we are moving to the differential pulse code modulation. Here in this DPCM, it will transmit A to D, it will undergo A to D conversion, but along with that, here we will not transmit or send all the samples that have all the samples. Here what we will do, here we will transmit only the respective difference between the respective sample and the predicted value. This predicted value is the past sample. So the difference between the present sample and the past sample is transmitted, and that is quantized and then encoded. But in the case of PCM, whatever the samples obtained at each and every instant, all those values will be quantized without considering the redundancy effect. It will quantize all the samples and then encode. So forming the redundancy, so shortage of large amount of bandwidth. So it uses large amount of bandwidth. So that's why in differential PCM, only the present sample value and the difference between the present sample value and the predicted value, that is the past value, both is taken, the difference is taken, and that is quantized and encoded. That is, here you can see, in DPCM, we will transmit only the difference between the samples. Unlike PCM, where the code words, each code word represents a sample value. Here, all the sample values will not be transmitted, only the difference between the samples will be taken into account. Now, coming to the block diagram of differential PCM, this is a DPCM transmitter section. In the PCM, you can see that we have only 3 blocks, sampler, quantizer, and encoder. But here, in order to eliminate the redundant samples, first we are taking the sample signal, and the past data, past information is stored in the prediction filter. So this prediction filter is used to reduce the quantization error. So other than this, the 3 blocks are as usual. And here we are using a comparator. Comparator compares the present sample value with the past sample value, and some error will be produced, which is called as E of NTS. And that error is sent to the difference between the samples is quantized, and you will get quantized output signal as E suffix Q of NTS. And that E suffix Q of NTS, which is a quantized error signal, is again stored in the prediction filter as a past sample. So here again this is applied, this is added with the X cap of NTS, where X cap of NTS is a predicted signal. This X cap of NTS plus EQ of NTS produces the prediction filter, produces the input to the prediction filter. So finally, at last, you can get that the prediction filter is a combination of predicted signal X cap and quantizer output, that is EQ of NTS. That data is stored in the prediction filter as a past sample. Now let us go through the analysis part. Here let the comparator output, what is the comparator output? Let the current sample be X of NTS and the past sample stored in the prediction filter be X cap of NTS. The difference between those two can be obtained from the comparator as E of NTS, that is written as equation 1. And next, that error signal is applied to the quantizer. So quantizer inbuilt, it has some sort of error we already discussed in the PCM, quantization error, that we are considering as E of NTS. So input to the quantizer is Q of NTS and quantization error is Q of NTS. Both are added to produce EQ of NTS. Where EQ of NTS is the output of the quantizer. So that is taken as equation 2. Next, now this EQ of NTS is added with the past sample or predicted signal to produce the input to the prediction filter. So that is XQ of NTS, which is equal to the sum of X cap of NTS and EQ of NTS. Here XQ of NTS is equal to X cap of NTS plus EQ of NTS. Here let us replace the quantizer output from equation 2 and substitute in equation 3. So let us replace this EQ of NTS equation 2 into equation 3. Then you will get xq of NTS is equal to x cap of NTS plus E of NTS plus Q of NTS. But here from the circuit you can see that E of NTS is x of NTS minus x cap of NTS. So if you take that x cap of NTS towards the right side, then x cap of NTS plus E of NTS gives you x of NTS. So this whole thing you can replace it as x of NTS. So you can get that xq of NTS is already I have written the same expression. And if you replace this x cap of NTS plus E of NTS as x cap of x of NTS, then the quantized error signal xq of NTS, or you can also call it as the input to the prediction filter. It can be written as the sum of x of NTS, that is the original sample, and Q of NTS, that is the quantization error. So you can conclude that here the quantized version of the signal xq of NTS is independent of the prediction filter characteristics. It is only dependent on the original sample value and the quantization error Q of NTS. Here remember that this quantization error can be either positive or negative. So finally you can conclude that xq of NTS is, that is the quantized version of the signal or the input to the prediction filter, is dependent only on the input sample and quantization error, and it is independent of the prediction filter characteristics. Now coming to the different DPCM receiver section, here just we have considered the equation 3, which represents the quantized sample as the sum of, in the equation 3 you can recollect the quantized version of error signal is represented as the sum of prediction sum of the past sample x cap of NTS or predicted signal and the quantization error output of the quantization. So the same equation here we are taken. By using this you can produce xq of NTS. So the DPCM signal is collected by the decoder, and decoder decodes and converts it into the quantized error signal, or you can say that the difference is produced here. The difference between the samples is produced, and that is added with the prediction filter. So that is added with the past sample. So once you add past sample to this, you can produce the output of the quantizer, that is xq of NTS. So same signal will be reproduced here, and that data is smoothened by the. So finally, the quantized, the prediction filter output. The prediction filter output is x cap of NTS, and the quantized error signal, that is EQ of NTS, are summed to give up the quantized version of the original signal. So same, this is the same mathematical expression which we have studied at equation 3 in the transmitter section. So with this you can conclude that the DPCM system efficiently removes all the redundant component, redundant samples or redundant bits by transmitting only the difference between the successive samples. The main difference between DPCM and PCM is that the redundancy problem in PCM can be eliminated by using differential PCM, and also the quantization error somehow reduced by using the prediction filter used in the feedback section. So with this we can conclude the concept of differential pulse code modulation system, and in the next class, in the next in the next module, we can discuss the module 7, that is about the delta modulation. Thank you everyone.